In this problem we are going to solve again the joint, basically butt joint. We are going to connect the two plates. So we'll just first of all write down a problem. So problem is two plates 200 mm by 8 mm of grade 410 are connected by 20 mm bolts using butt joint. 20 mm bolts using butt joint. Design the bolted connection to transmit a pull equal to the strength of the plate. Bolts are of grade 4.6. So this is a problem in which two plates 200 mm by 8 mm of grade 410 are to be connected by 20 mm bolt using butt joint. Now we need to design the bolted connection to transmit a pull that is equal to the strength of the plate. So grade of the bolt is also given there, and that is 4.6. So we'll solve step by step. First of all, we'll go through the given data, then we'll calculate the tensile forces. Once we calculate the tensile forces, then we'll go for the calculation of number of bolt and A distance, P distance, and that would be your final number of bolt. So we'll go ahead with this step number 1. So step number 1 is given data. So that's step number 1. So given thing is plate size, width of the plate, which is denoted by B, and that is equals to 200 mm. Then thickness of the plate, which is denoted by T, small t, and that is equals to 8 mm. Then plate material of the plate, or you can say FUB, which we already seen. So that is 410 Newton per mm square. And then diameter of the bolt, let us say it is denoted by small d, and that is equals to 20 mm. Now we'll go ahead with the step number 2. So that's all is given in given data. Width is given, thickness of the plate is given, FUB, and then diameter of the bolt. So now we'll go ahead with the step number 2. So step number 2 is to calculate tensile forces. So first of all, we need to go ahead with the required thickness of the cover plate, because you need to understand that whenever we go ahead to solve, or we need to joint it by a butt joint. So what does that mean? So let us say this is one plate, and let us say this is another plate, and since we need to join it with the help of butt joint, so we require, this is called as a one cover plate, and we require, this is called as a another cover plate. And here there would be certain bolts. So this is just to display what exactly the thing is going to be, and we need to calculate what is this number of bolt and what is the size of this plate. This is actually cover plate. So we need to just check cover plate as well as the number of the bolt, right? And this is called as a butt joint. So we'll go ahead one by one now. So required thickness of the cover plate, and that is given by 5/8 times thickness of the plate. 5/8 times thickness of the plate. So this is equals to 5/8 times thickness of the plate. So if we just calculate 5/8 times thickness is already given, that is 8 mm. So 5/8 multiplied by 8, so that is going to be 5 mm. So that is the required thickness we need to go with this cover plate, and that is the minimum thickness. We can provide more than that thickness of the plate. So providing cover plate of, let us say, 6 mm thickness. So you can write down here, providing cover plates of 6 mm thickness. And let us say we need to provide 2 bolts in one row. 2 bolts in one row. Suppose, let us say it is in plan. So let us say this is in plan. So in plan you will be going to see the cover plate like this, and this is the main plate. So this is basically cover plate. So suppose if you mark here center line, so in this case when we say 2 bolt in one row, so it means that like this. Okay, in that case you can see you will have like this. Okay, so we'll move towards our problem. So we can write down provide two bolts in one row, as I have shown you the diagram. So now according to the clause number 6.3.1 page number 32, which we already seen in earlier cases, earlier problem, so we need to first of all calculate the tensile force. So this is it. So what does it say? Again, design strength due to rupture of the critical section, and the design strength in tension of a plate, that is TDN, is given by this formula 0.9 AN FU divided by gamma M1, right? And what does this indicate? So this indicates that gamma M1 is the partial safety factor from table number 5, which is on the earlier page. Fu is the ultimate stress of the material, and that N is the net effective area. So gamma M1, to go ahead with the gamma M1, that is from this table number 5. So here gamma M1, you can see this is the resistance governed by ultimate stress, and gamma M1, which is 1.25. So gamma M1, this is 1.25. So I'll write down from clause 6.3.1 page 32 of IS 800. So we have this TDN is equal to 0.9 FUB-AN divided by gamma M1. Now here first of all we need to calculate AN here. So AN, it is the net effective area. So if we talk about the net effective area, so that is equals to B minus N D0 multiplied by T. So this is again on the same page. You can see the next page you have this N equals to B minus N dN into T. That is on the next page, that is page number 33. Now we got here width, we got the thickness, we got the number as we are saying, that is in the 2 bolts in one row, and then we are saying that D0. D0 is the the clearance, bolt clearance. So as you know here, D0 will be equals to D plus 2. So that is 20 plus 2, that is the clearance we considered hole diameter, and that is 22 mm. So now therefore we'll get AM, that is B, you got your width, that is 200 mm. So this is equals to 200 minus N, because we are saying 2 bolts in one row. So 2 multiplied by D0, it is 22 mm, and multiplied by thickness, as you know, thickness of the plate. Okay, thickness, not of the thickness of the cover plate, but the thickness of the plate. So thickness of the plate, that is 8 mm here. So now if you just put this AN into our TDN formula, so therefore we will get TDN, that is equals to 0.9. FUB, we got here FUB, that is 410. So 410, as you know, ultimate stress of the plate material, that is the FUB. So AN you got, you can just directly put this value, 200 minus 2 into 22 multiplied by 8 and divided by gamma m1 as gamma m1, that is 1.25. so if you solve this, you will get TDN, that is equals to, that is the tensile force to be carried by the plate. How much tensile force that plate can carry. Okay, and for that you will get around 368.4 kilonewton. So that's the value of TDN. Now in the next step, we will calculate the number of bolts and pitch in the next video. So we'll see this thing in the next video, where we will be going to solve strength of bolt in bearing, strength of bolt in double shear.